Samuli Toivola from Nokia, and he's coming up at this point. Samuli is the lead hardware architect for OpenEdge and OpenRack products, and he joins us from Finland. Start now. No. Let's see. What's this?
Okay, let's start then. My name is Samuli Toivola and I'm coming from Nokia, and today I will talk you about direct liquid cooling for open edge servers and study what we have done for that product at Nokia. Let's start from presentation slide about current status of current air-cooled open edge server and how it looks like. You can see that this is a kind of fan-cooled system, and what is special with open edge, what we all know, is that it goes up to 55 degrees Celsius, so it's full NEPS compliant in cooling point of view. And what else I can say, kind of key design specifications of server are that we have airflow up to 100 CFM in 1U server's LED and 160 CFMs in 2U server's LED when the fans are at maximum speed. We also support both front to rear and rear to front airflow options. And of course we have fan control algorithm with uses as low fan speed as needed for cooling of system in air-cooled system. And in this presentation I show also those maximum power levels what you can reach with this air-cooled system, even up to 500 watts in 1U server and 800 watts in 2U server. Okay, and to further improve from this present status, we have done a proof of concept and study about liquid cooling. And of course, when starting that kind of air-based heat transfer, what is dominant in IT equipment, there are those technology limitations, physical limitations, and those are limiting the heat density and maximum power of system, and with liquid cooling we can overcome those limitations. In Nokia side, we think that we need to go with evolutive approach, and we have set some key requirements for going advanced cooling solution. And first one is that full compatibility need to be kept for existing products what we have in open edge, like servers, front hall gateways and other products there. And second one, what is very important, is that all interfaces, all maintenance must be possible from front side of chassis when chassis is installed to the system, so no need to go to the rear side of chassis in normal operation. And of course fail-safe and fault-proof design must be kept in the mind. Last year we released that kind of white paper about advanced cooling solutions and showed the benefits what we can reach with that kind of cooling solution, and this presentation is then showing some testing and results what we have reached with our proof of concept at Nokia. So here you can see server with evac heatsink, and in this study, and we have used pumped direct chip to liquid cooling for CPU of this server. And here you can see we remove heatsink and replace that with cold plate, and we removed one fan and put those liquid fluid connections there. And in lower picture you can see how we slightly modified chassis to support those connections. No big changes, but kind of evolution from original open edge design. And for this proof of concept we selected bigger 3U chassis to be modified and 5 server sleds in system. Here you can see our simulation fixtures how the fluid goes there in server level and in chassis level. You can see those pipes inside server. You can see those manifolds in chassis level, and lower rightmost picture is showing pressure difference between inlet and outlet pipe of server. And here you can see that we really have some physical implementation, so pictures about server, picture about chassis and those chassis manifolds showed in rightmost picture, and in front side you cannot see any difference compared to the air-cooled solution. It's exactly same. We did not need to do any changes for server basic function and basic features in mechanically. So it was quite straightforward modification in this proof of concept design. And then some results shown here. First thing is that in this proof of concept we moved from our standard 185 watt CPU to 270 watt CPU. So quite significant increase in CPU power. And then we actually tested with several liquid temperatures, but this figure is shown with liquid temperature, inlet temperature of 25 degrees Celsius. And you can see that there is actually no difference between different ambient temperatures to CPU temperature when running full 270 watt power in each server. And there was very minimum pressure drop in system with 5 servers, and very good thermal resistance values were measured in that testing. And then let's go to the second key finding what I can show here. This is that with liquid cooling we can actually reduce very significantly fan speeds what we have for DRAMs and SSDs what are still using air-cooled cooling, and actually you can see that it's about 10 decibel decrease in acoustic noise in system. And actually even we just removed one fan for those hoses and connectors. We tested with only 2 fans in system, and it was easy to cool system, even highest ambient what we tested, and it even further reduces acoustic noise. So with this kind of solution you can see those benefits that you can easily cool CPU with very high power. You can increase processing power of system, and at the same time you can reduce acoustic noise, what is quite important in outdoor systems. If the system is somewhere where people can walk, you cannot have too noisy system there. And some comment about reliability. We made that kind of proof of concept, and even with that kind of let's say high volume manufacturing products, we did not have any problem during different testing phases, taking servers out, let's say tens or hundreds of times from system with different amount of servers, with different power levels of servers. No issues all the time. Cooling was very even between different servers. And then what kind of opportunities we see for edge if we go to that advanced cooling. Of course, savings of energy consumption are quite evident. We can move heat much more efficient way, and with higher temperature of liquid, and with that way we can enable free cooling in many environments where it's not possible with air heat transfer. We can increase system density. We can put more servers to the same rack, or we can put more power to the single server. And with that way, we can increase computing capacity of system. And then we can decouple computational power from cooling power consumption. And this enables some new ways to maneuver with that heat. We can, for example, have some heat accumulator. We can cool when energy cost is lower with that way, or many other options what we discussed in white paper more in details. And then of course with lesser fans we can reduce acoustic noise and lower server power consumption. And then one finding is that there is better thermal stability, so no that kind of fast transients in thermal temperature of CPU, and of course this can increase reliability of CPU. And then, as said, this is study phase, not product or released, and idea is that we continue with different possible approaches, and maybe test also other ways to enable liquid cooling or even two-phase cooling for open edge. And then we need to find answers for a few questions, how that kind of deployment is easy and possible with liquid cooled systems. 10 components what are not shown in this presentation, like coolant distribution unit, heat exchangers, and all parts of hydraulic hardware need to be then further studied. And then other components in systems like DIMMs and PCI cards, should we go to the liquid cooling also for those parts? Those kind of things need to be analyzed further. Okay, here is current portfolio of Nokia products in open edge, including one-use servers, two-use servers, front-haul gateways, and chassis, RMCs, power supplies, and then call for action. I think that in this presentation I want to call other companies who are working in this kind of liquid cooling and components related to that to participate with us to make all details in design to be ready if and when we need to make that kind of liquid cooled version of open edge server, chassis and system as a product. So thank you about listening me.
We have time for a few questions if there's any from the audience.
I have one question. You said you're talking about decoupling of the cooling methodologies in the server for computation and for also the power levels. Does it mean that there will be a separated cooling loops for these two hardware equipment within the server?
No, the idea in that sentence was that we can actually, for example, use that heat, store that heat and cool it when electricity is having lower cost, like it typically is in Europe, that in night time it can be even zero cost. If we, with liquid cooling it makes that kind of things much easier, and as said there are much more information about that kind of possibilities in white paper what we released last year.
Okay. Thank you. Thanks.
So do you address the requirements for the cooling system in terms of the pumps and the pump reliability? Is that part of the rack environment that you need to consider?
We have focused quite much to the server analysis, and those are some things that what was mentioned that will be next steps if and when we go to the further. So we have not that much analyzed what we will need in rack level, but for example in this show there are a lot of different rack vendors having that kind of liquid cooling
Yeah,
products.
I would believe they're mostly for big data centers, right? But this
Those
is
are
this
those
is
are bit,
a small.
yeah,
a
we need
small
something
engagement.
smaller.
Yeah,
Yes, that's
okay.
true.
And
It's-
another question would be, do you have customers who are actually asking for servers of these power levels on the edge?
You mean that 400 watt, 500 watt power levels, what I mentioned? Yeah, it's not actually so that customer is asking servers for that power level, but they are asking some capacity of, for example, vRAN or Cloud RAN deployment, and it actually goes to the quite high power if those bigger capacity requirements are filled.
Okay, great, thank you.
Thank you.
Any last questions? I think we'll move on to our next speaker. Thank you, Samuli.
Thank you.